Pluto was demoted, but then it became far more interesting. That distant speck we thought was a simple ball of ice was hiding a world of astonishing complexity. For decades, it was just a blurry dot at the edge of our maps, a footnote in astronomy textbooks. Then, the New Horizons spacecraft raced past it in 2015, and everything we thought we knew was turned upside down. The images it sent back revealed a landscape of bizarre beauty and profound mystery. By the end of this journey, you will understand why this tiny world is now one of the greatest puzzles in our solar system. We are about to explore 25 unexplained enigmas that defy our basic understanding of cold, distant worlds. How can a glacier flow where temperatures are hundreds of degrees below zero? What unseen force is keeping a frozen heart beating? The mission was just a fleeting glimpse, but it opened a door to secrets we are only beginning to unravel. What does it mean for a world to be truly alive? The first and most iconic mystery is staring right back at us from those images, a vast pale heart etched onto the face of the world. This is Tombaugh Regio, a heart-shaped feature over 1,000 miles wide, and its left ventricle holds the key to Pluto's restless nature. That region, named Sputnik Planitia, is an enormous basin filled not with rock, but with a slowly churning glacier of solid nitrogen, carbon monoxide, and methane ice. Its surface is eerily smooth, broken not by ancient scars but by strange polygonal patterns like a cosmic cracked mudflat. And here lies the first profound puzzle. This immense plain shows almost no impact craters. In the solar system, crater counts are like a clock. Heavily cratered terrain is old, having endured billions of years of bombardment. A smooth surface is young, recently resurfaced, its history wiped clean. Sputnik Planitia is geologically young, perhaps less than 10 million years old. This is an eye blink in cosmic time. The question it screams is simple yet revolutionary. What force is actively repaving this frozen plain? Pluto is tiny and incredibly far from the Sun. It should be a dead, frozen billiard ball, its internal heat lost to space eons ago. Yet something beneath that icy heart is beating, providing enough warmth and energy to reshape the landscape. Scientists are chasing two leading theories. The first points to the slow, persistent decay of radioactive elements in Pluto's rocky core, a faint radiogenic warmth that might still be enough to stir the pot. The second, and far more tantalizing, is the possibility of a deep, subsurface ocean of liquid water, insulated by a thick shell of ice. The gravitational tug of Pluto's large moon, Charon, could flex this ocean, generating heat through tidal forces, much like Jupiter's gravity heats the moons Europa and Io. But this creates another layer of mystery. If there is an internal heat source, why is all this dramatic activity so fiercely concentrated in one specific spot? Why is the heart the only place that seems to be alive? That concentration of activity points directly to the second great mystery, one that moves and flows before our very eyes. On Pluto, glaciers are not frozen relics. They are rivers in slow motion, carving valleys and filling basins, but they are made of something far stranger than water ice. These are glaciers of solid nitrogen, methane, and carbon monoxide, flowing across the landscape at temperatures close to 400 degrees below zero. The New Horizons images show them spilling from highlands into Sputnik Planitia, their surfaces marked by clear flow lines, just like the glaciers you would find on Earth in Greenland or Antarctica. They have even carved valleys into the water ice bedrock, proving they are powerful, persistent geological agents. This presents a staggering paradox. On our planet, glacial flow is driven by the pressure of immense weight and the slight warmth near the melting point of ice. But nitrogen ice at Pluto's temperatures is harder than steel. It should be brittle, immobile, locked in place for eternity. So what unseen force is making these exotic ices behave like soft putty? The answer seems to lie in a combination of extreme cold and subtle warmth. While the surface is unimaginably frigid, the internal heat we discussed may create just enough of a temperature gradient. At depths of just a few hundred meters, the nitrogen ice might reach a point where, under the immense pressure of overlying layers, it can actually soften and flow in a process called solid-state convection. Think of it not as melting, but as the entire icy mass slowly deforming and oozing like cold honey over geological timescales. This leads to the even wilder idea of cryovolcanism, where these ices might not just flow but erupt. Imagine not a volcano of molten rock, but a volcano of slushy, pressurized nitrogen or methane, bursting from a vent and freezing instantly into strange, mountainous formations. We see candidate structures on Pluto like Right Mons, a massive feature with a central depression that looks eerily like a volcanic caldera. If this is a cryovolcano, what geological engine creates the pressure needed to force these frozen materials to the surface? Is it the expansion of a subsurface ocean as it freezes, or the slow build-up of gases from decaying radioactive heat? The fact that we are even asking these questions about a small, distant world rewrites the rules of planetary geology. These flowing glaciers and potential ice volcanoes paint a picture of a world in motion, but they are not the only sculptors at work. Far from the churning heart, along Pluto's jagged equator, lies a landscape so utterly alien it seems ripped from the pages of a dark fantasy novel. This is the bladed terrain of Tartarus Dorsa, a vast region where the ground itself has grown teeth. Imagine standing on a plain of solid methane ice, but instead of a flat, frozen expanse, you are surrounded by colossal, razor-sharp ridges. These are not simple hills or cracks. They are colossal blades, some soaring as high as skyscrapers, all aligned in the same direction and spaced with an eerie regularity, like the spines on some monstrous fossilized creature. The sheer scale and uniformity of these structures defy simple geology. They look less like natural formations and more like something deliberately, artfully carved. So what cosmic force could possibly create such a precise and terrifying landscape? The leading theory points to a process both delicate and destructive called sublimation. This is where a solid, like methane ice, turns directly into a gas without ever becoming a liquid. On Pluto, with its whisper-thin atmosphere and extreme temperature swings, the sun's weak light can still provide enough energy to make this happen over millions of years. Scientists think that as the methane ice sublimates, it leaves behind tougher, more resistant material, perhaps water ice or complex organic compounds that form the hard, jagged spines. The surrounding, softer ice vanishes into the thin air, leaving these towering blades behind. But this explanation, while logical, only deepens the mystery. Why are the blades so uniformly tall and so perfectly aligned? What controls their precise spacing? On Earth, we see smaller versions of this in penitent snow formations in the high Andes, but Pluto's blades are on a monstrous planetary scale. This suggests an environmental rhythm far more complex than we anticipated. It hints that Pluto's climate, over million-year cycles, undergoes dramatic seasonal changes we are only beginning to model. Perhaps the angle of the sunlight, the pressure of the tenuous atmosphere, or even global patterns of ice deposition work together in a precise, repeating dance to sculpt this nightmare terrain. The bladed landscape is not a static monument, it is a snapshot of an ongoing, epic process of erosion, a fossilized record of Pluto's atmospheric breathing written in ice and shadow. If we could read that record, what stories of climatic upheaval would it tell? The bladed terrain reveals a world sculpted by its atmosphere, but that atmosphere is itself a profound enigma. Pluto's thin, hazy air should not exist at all, at least not in its current form. When the New Horizons spacecraft looked back at Pluto, silhouetted against the sun, it captured a breathtaking sight. the tiny world was enveloped in a luminous blue halo of haze extending over 100 miles above the surface. This was our fourth great mystery. A planet so small and so cold should have an atmosphere that has long since frozen solid and collapsed onto the ground, especially as Pluto journeys to the farthest, coldest point in its 248-year orbit. Yet the haze persists, and the atmospheric pressure, while minuscule compared to Earth's, is actually higher than predicted. Something is actively pumping gas into this tenuous envelope, preventing its total collapse. The source of this replenishment is a major puzzle. The leading suspect is the slow, constant sublimation of surface ices, particularly nitrogen ice from the heart of Sputnik Planitia. As the weak sunlight warms this ice, even at 4 billion miles away, molecules escape into the sky, but the math is tricky. This process should slow to a crawl as Pluto recedes from the Sun, yet the atmosphere seems resilient. This hints at a hidden reservoir, a global layer of volatile ices just beneath the surface that can feed the atmosphere over long timescales, or a thermal inertia in the ice itself that delays the freezing process. Even more puzzling are the haze layers themselves. They are not a uniform soup, but a series of over 20 distinct horizontal bands stacked like the layers of a cake. These are not clouds in our familiar sense. They are likely composed of tiny particles called tholins, complex organic molecules that form when methane and nitrogen in the upper atmosphere are zapped by solar ultraviolet radiation. These particles then slowly snow down, painting Pluto's surface with its characteristic reddish-brown color. But what creates such orderly, separate layers? The answer may involve gravity waves, ripples in the atmosphere caused by winds flowing over Pluto's dramatic mountains and valleys, creating stable zones where haze can accumulate. Or it could point to an unknown chemical process, a rhythmic production of these particles at specific altitudes. The presence of this extended haze also creates a bizarre thermal inversion. Normally, air gets colder as you go higher. On Pluto, the haze particles absorb what little sunlight there is, actually making the upper atmosphere dozens of degrees warmer than the surface far below. This trapped heat might be a key part of the atmospheric engine, helping to keep it puffed up and stable against the relentless pull of gravity. So we are left with a fragile, beautiful, and defiant system. A world actively breathing its ices into a structured, glowing haze, an atmospheric ballet sustained by hidden reservoirs and subtle chemistry, all against the impossible cold of deep space. What does it take for a world to hold onto its sky? This delicate atmospheric ballet leads us directly to a core contradiction, the fifth mystery on our list. For years, astronomers used a clever trick to study Pluto's air, watching how starlight flickered as the distant world passed in front of distant stars. These stellar occultations, observed from Earth, told a surprising story. They suggested Pluto's atmosphere was not just persisting, but actually growing thicker and expanding throughout the 1980s and 90s, even as the planet moved away from the warmth of its closest approach to the Sun, called perihelion. The logical explanation seemed to be a thermal lag. Just as the ocean stays warm into the autumn after a hot summer, Pluto's vast reservoirs of surface ice might take decades to respond to the changing seasons, continuing to sublimate and puff up the atmosphere long after the peak heat had passed. This painted a picture of a resilient, even growing gaseous envelope. Then New Horizons arrived in 2015, roughly a quarter century after that last perihelion. Its precise measurements delivered a shock. The atmospheric pressure at the surface was far lower than many of the expanding atmosphere models had predicted. It was not a robust, growing shroud, but a tenuous haze clinging to existence. This discrepancy is the heart of the pressure puzzle. Was the atmosphere caught in the act of a dramatic collapse, or were our initial interpretations simply wrong? Two competing theories now grapple with the data. The first holds that the sublimation engine is indeed winding down. As Pluto journeys farther into the deep freeze of its 248-year orbit, the nitrogen ice at Sputnik Planitia is finally beginning to freeze out, its molecules returning to the surface frost. The atmosphere we saw was perhaps at its peak, and we are now witnessing the start of its long, slow fade into winter hibernation. The second theory is more complex. It suggests that what we measured from Earth was not a simple global increase, but a localized phenomenon. The heart-shaped Tombaugh Regio, with its immense reservoir of volatile ice, might have been tilted toward Earth during those earlier occultations. We were measuring the atmosphere above a particularly active geyser of sublimation, not the global average. New Horizons, by providing a full global snapshot, gave us the true, thinner picture. The terrifying truth is we do not know which scenario is correct. We have only a single, fleeting data point from a spacecraft, a snapshot in the middle of a seasonal epoch that lasts longer than the United States has been a nation. To understand the true rhythm of Pluto's breath, we would need to watch it for centuries. Does its atmosphere swell and collapse dramatically with each orbit, or does it maintain a fragile, steady state fed by hidden underground sources? This single question holds the key to predicting the future of its glaciers, its hazes, and the very habitability of its potential subsurface ocean. The pressure is not just a number, it is the pulse of the entire world, and we have only felt a single confusing beat. While the atmosphere's pressure remains a puzzle, its chemistry paints the surface in a startling palette of color. Along Pluto's equator, adjacent to the bright expanse of the heart, lies a sprawling, dark stain known as Kuiper Macula. This is our sixth mystery, a region the color of rust or dried blood, stretching over 1,800 miles, nearly the width of the entire United States. Its dark, reddish hue forms one of the most dramatic visual contrasts in the solar system, sitting right beside the brilliant white of Tombaugh Regio. This is not a shadow or a trick of the light. It is a vast deposit of complex organic molecules called tholins, and their presence and precise location raise profound questions about Pluto's past and present. Tholins are not alive, but they are the cosmic precursors to life's building blocks. They form through a simple yet powerful recipe. Ultraviolet radiation from the distant sun, or even cosmic rays, strikes simple molecules in Pluto's atmosphere like methane. This high-energy bombardment breaks those molecules apart, and the fragments recombine into larger, more complex carbon-rich chains. These newly formed particles are the tholins. They are too heavy to stay aloft forever, and they eventually snow down, coating the surface in a thin, reddish film. This process should, in theory, happen everywhere sunlight reaches. So why is Kuiper Macula so exceptionally dark and concentrated, while the heart right next to it remains dazzlingly bright? One possibility is age. Kuiper is heavily cratered, indicating it is one of Pluto's oldest terrains, a primordial landscape that has been collecting this organic snowfall for perhaps billions of years. The heart, by contrast, is geologically young and active. The constant churning and renewal of its nitrogen ice glaciers may be constantly burying or recycling any tholins that fall there, effectively keeping it clean. But another, more active mystery emerges. Could Kuiper Macula be a place where tholins are not just accumulating, but are actively being created on the ground? Some scientists speculate that seasonal changes might play a role. When Pluto's poles tilt toward the sun during their long seasons, frozen methane on the surface there might sublimate, travel through the atmosphere, and then refreeze in the colder equatorial region like Kuiper. This would deliver fresh methane ice to the surface, where it could then be directly irradiated by sunlight and transformed into tholins in place, creating a self-reinforcing darkening cycle. This stark duality, the bright, active heart and the dark, ancient stain, is a direct conversation between Pluto's internal geology and its external climate. One region speaks of churning renewal from within, while the other whispers of eons of passive accumulation from above. Together, they form a planetary scale canvas where processes of creation and preservation are locked in a silent, visible balance. What ancient events decided that this particular stretch of ground would become the keeper of Pluto's organic history? The dark organic stains of Cthulhu macula speak of a surface shaped by the sky above, but just beyond its borders lies a texture that seems to defy the very nature of solid ground. In certain regions, most notably within the bladed terrain of Tartarus Dorsa, the landscape transforms into something truly otherworldly. It is a pattern dubbed the snakeskin terrain, a vast expanse where the surface of Pluto is etched with a network of interlocking, scaly ridges and pits, each one several miles across. From high above, it looks less like geology and more like the skin of a colossal, fossilized dragon or the bark of an ancient petrified tree. This cellular pattern is not random. It is a repeating, almost artistic arrangement of shallow depressions surrounded by raised, polygonal borders, creating a texture unlike anything seen with such clarity on any other world. The leading explanation points to a slow, churning process happening deep within the ice itself, a phenomenon called solid-state convection. Imagine a pot of thick soup on a very low simmer. The warmer material at the bottom, being less dense, slowly rises in plumes toward the surface. Meanwhile, the cooler material at the top sinks back down in sheets, creating a gentle, continuous overturning motion. On Pluto, the soup is a thick layer of solid nitrogen ice, and the heat source is the faint warmth from the dwarf planet's interior. Over millions of years, this convection could organize the ice into these regular, rising and sinking cells. The raised ridges might mark the boundaries where cooler ice is descending, pulling the surface down slightly at the edges of each cell, while the pits could be the centers where slightly warmer, buoyant ice is upwelling. This theory is elegant, but it immediately raises a deeper question. Convection occurs in many materials, from Earth's mantle to the atmosphere of the Sun. So why does this process on Pluto produce such an exquisitely detailed, widespread, and unique reptilian skin? Why don't we see this exact pattern in the nitrogen ice of other distant bodies, or even in Earth's own polar ice caps? The answer may lie in the specific recipe of Pluto's ice. This is not pure nitrogen. It is a mixed slurry containing methane and carbon monoxide ices as well. Each of these materials has slightly different properties: how they flow, how they conduct heat, at what temperature they soften. This exotic mixture might convect in a uniquely lumpy, textured way, creating these distinct cellular features. Furthermore, the extreme cold and the incredible slowness of the process might allow the pattern to develop with a perfection and uniformity that faster, warmer systems cannot achieve. It is a geological fingerprint, a direct result of Pluto's particular blend of ices, its specific internal heat, and its profound patience. The snakeskin is not a scar or an impact site. It is a living portrait of the dwarf planet's interior, slowly, silently breathing, its hidden rhythms made visible on the surface for the first time. What other secrets are written in this frozen, cellular script? The snakeskin terrain reveals a world churning from within, and that hidden heat may have once broken through the surface in the most dramatic way possible. Towering over the southwestern edge of Sputnik Planitia are two colossal and enigmatic mountains, Right Mons and Pickard Mons. These are not jagged peaks carved by impacts or tectonics. Each one is a broad, gently sloping dome over 100 miles across and several miles high, and each is crowned by a deep, central depression like a vast, frozen cauldron. Their form is hauntingly familiar to planetary scientists. They look exactly like volcanoes, but on Pluto, volcanoes do not spew molten rock. They would erupt a frigid, slushy mixture called cryolava, a slurry of water ice mixed with ammonia, methanol, or other antifreeze compounds that can keep water liquid at temperatures hundreds of degrees below zero. Wright and Pickard Montes are our strongest candidates for cryovolcanos in the entire solar system, and they present a monumental puzzle. If these are indeed volcanoes, what incredible force could have melted the hardest substance on Pluto, which is water ice, and then pushed it up through miles of frozen crust to create mountains. On Earth, volcanic heat comes from a molten mantle and radioactive decay. Pluto, being so small, should have lost that internal furnace eons ago. Yet the apparent lack of impact craters on their flanks suggests these features could be relatively young, geologically speaking. This forces us to consider two staggering possibilities. The first is that these are ancient relics, frozen monuments to a bygone era when Pluto's core was still hot, perhaps from the violent energy of its formation or the rapid decay of short-lived radioactive elements. They would be dormant sentinels, their internal fires long extinguished. The second possibility is far more thrilling. What if they are evidence of much more recent or even ongoing activity? The heat needed to melt water ice on Pluto could only come from a powerful and persistent source. The prime suspect is that hidden subsurface ocean, kept liquid by a cocktail of antifreeze compounds and warmed by the steady decay of radioactive elements in the core. The gravitational tug of war with Charon could then provide the extra-tidal heating needed to create pockets of slushy cryomagma. Imagine the eruption. Not with fire and ash, but with a slow, viscous ooze of icy mud, perhaps tinged with ammonia, spreading across the landscape and freezing into these immense dome-shaped structures. The central depression might be a collapsed caldera, where the ground sank after the subterranean chamber emptied. The mystery of Wright and Pickard Mons is not just about their origin, but about the very definition of a living world. Does geological life require molten rock and a thick atmosphere, or can it persist in the silent, frozen dark, powered by radioactivity and tidal friction, building mountains of ice instead of stone? Those potential ice volcanoes point to a fire burning in the cold, and that brings us to the fundamental mystery that fuels all the others. Pluto is simply too small. A world with only 1/600th the mass of Earth and so far from the Sun should have become a geologically dead, frozen relic billions of years ago, its internal heat long since radiated away into the void. Yet everywhere we look, from the uncratered plains to the flowing glaciers to the towering mountains, we see a landscape that has been reshaped in the very recent geological past. This forces a single, unavoidable question. What is keeping Pluto warm? The answer is not simple, because the obvious sources of heat all seem insufficient on their own. The first candidate is primordial heat, the leftover warmth from the violent collisions that built the dwarf planet over 4 billion years ago. For a larger world like Earth, this heat can linger, powering plate tectonics and volcanoes. But for a small body like Pluto, this heat should have escaped into space relatively quickly, perhaps within the first billion years. It is a fading ember, unlikely to power present-day activity. The second source is radiogenic heat, the steady, persistent warmth generated by the decay of radioactive elements like uranium, thorium, and potassium locked within Pluto's rocky core. This is a slow, reliable furnace, and it is almost certainly still active today. The problem is one of scale. Based on our best estimates of Pluto's size and composition, the heat produced by radioactive decay alone is likely just a tiny background trickle. It might be enough to keep a deep ocean from freezing solid, but is it really enough to drive massive glacial convection, resurface entire plains, and potentially fuel cryovolcanism? Many scientists are skeptical. This leads us to the third and most dynamic possibility, tidal heating. Pluto is locked in a gravitational dance with its largest moon, Charon. They are so close in size that they orbit a common point in space between them, forever facing each other like partners in a slow, cosmic waltz. This intimate connection creates friction. As Pluto's shape is subtly stretched and squeezed by Charon's gravity, internal layers rub against each other, generating heat. This process is what keeps the subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus liquid. But here is the catch. For tidal heating to be significant, the orbits need to be eccentric or slightly oval-shaped. the constant change in distance creates a stronger, rhythmic flexing. Pluto and Charon's orbits today are nearly perfect circles. They are too stable, too settled to generate much frictional warmth now. However, their dance may not have always been so serene. In the distant past, their orbits could have been much more eccentric, perhaps due to a giant impact or the gravitational influence of other bodies. If that were the case, tidal heating could have been a powerful engine in Pluto's youth, potentially jump-starting its geological activity and even helping to maintain a subsurface ocean. The heat from that violent past could still be slowly leaking out, providing a delayed boost to the present. So we are left with a frustrating and fascinating puzzle. No single source seems adequate. The solution may be a combination, a little radiogenic heat to maintain a liquid ocean, a memory of past tidal heating to provide an extra push, and perhaps even exotic chemical reactions within the ice itself that release energy. Or, more intriguingly, our entire understanding of how heat moves through small, icy worlds could be flawed. Could Pluto's thick, insulating shell of water ice be far more efficient at trapping internal warmth than our models predict? Is there a hidden, more potent radioactive element mix in its core? The search for Pluto's hidden furnace is not just about solving one mystery. It is the key that unlocks all the others, the reason why a tiny world at the edge of darkness refuses to die. Pluto's hidden warmth might explain the geology of the world itself, but it does nothing to calm the frenzied dance of its smaller companions. Orbiting the central binary of Pluto and Charon are 4 tiny, enigmatic moons: Styx, Nix, Kerberos, and Hydra. They are not serene satellites following neat, circular paths. Instead, they exist in a state of perpetual chaos, tumbling through their orbits in a manner that defies simple prediction. Their motions are so erratic and unstable that if you tried to calculate their exact positions a few years from now, your predictions would become useless. This is not a minor orbital quirk, it is a fundamental property of their existence, driven by the complex gravitational field of the double planet they call home. The primary gravitational force in the system is not a single point, but the shifting balance between Pluto and Charon as they whirl around their common center of mass. This creates a dynamic, lopsided pull on the little moons, constantly tugging them in different directions and preventing them from settling into stable, predictable rotations. They do not spin like Earth's moon, with one face forever locked toward their planet. They tumble, wobble, and flip, their poles and equators trading places over time in a dizzying celestial ballet. This chaotic environment presents our 10th great mystery. How did these fragile moons even form, and how have they survived in such a violent neighborhood without being torn apart or flung into the void? The leading theory connects them to the system's violent birth. Most astronomers believe Charon itself was created from the debris of a cataclysmic collision between a young Pluto and another large Kuiper Belt object. The 4 small moons could be leftover fragments from that same ancient crash, pieces that were tossed into orbit and have been dancing chaotically ever since. Yet an alternative theory suggests they could be captured objects, wandering Kuiper Belt denizens that Pluto's gravity snatched long ago. Their appearances deepen the puzzle. Despite their small sizes, each only tens of miles across, they are surprisingly bright, reflecting much more light than expected. This suggests surfaces coated in relatively clean water ice, which should darken over time from radiation and tholin snowfall. Their brightness implies either recent resurfacing from some unknown process or a composition that actively repels contamination. Even their shapes, glimpsed only briefly by New Horizons, add to the confusion. Nix, for instance, appeared to be a reddish, elongated world with a puzzling dark spot on one face. Kerberos, meanwhile, was much darker than its siblings, a sooty outlier in a family of bright objects. The chaotic tumbling of Styx, Nix, Kerberos, and Hydra is more than an orbital curiosity. It is a direct echo of the system's violent origins, a live demonstration of the gravitational storm that rages around the binary heart of this distant kingdom. Their survival is a testament to a delicate, chaotic balance, and their unexplained brightness is a silent question about processes we have yet to imagine. What other secrets are tumbling in that darkness, just beyond the glow of the frozen heart? The chaotic waltz of the small moons is a direct consequence of the central gravitational truth of this system. Pluto is not a solitary king. It rules in partnership with Charon, a moon so massive it does not truly orbit Pluto in the traditional sense. Together, they form a binary planet, a double world locked in an eternal embrace. The center of their dance, the point they both circle, is not inside Pluto but in the empty space between them. This barycenter, as it is called, lies over 600 miles above Pluto's surface, a silent pivot point in the void around which both bodies swing. This equal partnership is the first layer of our 11th mystery, the binary planet paradox. How did such a perfectly balanced system come to be, and what does this intimate relationship mean for Pluto's very nature? The leading theory is one of cosmic violence, a Genesis story written in gravity and debris. Most astronomers believe that in the early, chaotic days of the solar system, a proto-Pluto, still forming from the icy rubble of the Kuiper Belt, was struck a glancing blow by another large object, perhaps nearly its own size. This titanic collision would have been catastrophic, vaporizing immense amounts of material and spraying a ring of molten and solid debris into orbit around the wounded survivor. From this glowing, swirling disk of wreckage, Charon coalesced, much like how Earth's moon is thought to have formed from a similar giant impact. This explains their shared composition and the strange, clean, angular momentum of the system. But the details of that ancient cataclysm are frustratingly murky. The impact had to be just right, not a head-on smash that would have obliterated both bodies, nor a gentle graze that would have done little. It had to be a precise, off-center collision that imparted exactly the right spin and ejected exactly the right amount of material to form Charon. Furthermore, the resulting system is remarkably clean and orderly. The four small, tumbling moons add complexity, but the core binary itself is now perfectly tidally locked. Pluto and Charon always show the same face to each other, like two dancers forever holding hands, never looking away. How did they achieve this perfect lock so completely? The process of tidal locking usually takes time as gravitational forces slowly break a moon's rotation. For Charon to be so perfectly synchronized suggests either an incredibly efficient process or that the system was born much closer to this locked state than we can easily model. Did other, now vanished moons help drain away excess energy? Was the initial disk of debris far more influential in breaking their spins than we realized? This binary relationship is not just a historical footnote. It fundamentally shapes the environment of both worlds. The gravitational tug of war between them is the architect of the chaos we see in the smaller moons. It also influences Pluto's interior, potentially providing the tidal heating that may keep a subsurface ocean liquid. Think of it as a constant, gentle massage from a partner, flexing the interior and generating warmth through friction. This partnership also affects Pluto's orientation in space. The combined gravitational pull of Charon likely helped to reorient the entire dwarf planet, possibly explaining why the massive, low-lying basin of Sputnik Planitia sits directly opposite Charon in the sky. It is as if the heart of Pluto was drawn to forever face away from its partner, a frozen testament to their gravitational bond. So we are left with a pair of worlds born from a single, shattering instant, now dancing a flawless, silent duet in the dark. The binary planet paradox asks us to reconsider what a planet can be. It is not always a solitary ruler. It can be one half of a whole, its history, climate, and very geology forever intertwined with another. The mystery of their formation is the mystery of their present, a single event billions of years ago that set the stage for every glacier, every mountain, and every breath of haze we see today. What other binary kingdoms born from similar violence might be waiting undiscovered in the outer dark? That gravitational dance between Pluto and Charon sets the chaotic rhythm for everything around it, and no moon follows a stranger beat than Hydra. This tiny, irregular world, no more than 30 miles across, is caught in a frantic, dizzying spin. It rotates on its own axis once every 10 hours, yet it takes a full 38 days to complete a single, lazy orbit around the binary center of the system. This mismatch is our 12th profound mystery. In a stable, mature system, moons become tidally locked, their rotation perfectly synced to their orbit, always showing the same face to their planet, just as our moon does to Earth. Hydra is anything but locked. It is tumbling wildly, a celestial gymnast spinning furiously as it swings slowly around the ring. This bizarre behavior defies the quiet order we expect from orbital mechanics. What force could possibly keep this little moon whirling so fast against the steady braking pull of gravity? The answer is not a single force, but a complex symphony of pushes and pulls from its entire family. Hydra is not dancing alone. It is in a gravitational conversation with its siblings, particularly the larger moon Nix. Scientists suspect these moons are caught in what is called a resonance, where their orbital periods are simple ratios of each other. For every one orbit Hydra makes, Nix might make 3 or 4. These periodic gravitational nudges, like a child being pushed on a swing at just the right moment, can pump energy into Hydra's rotation, keeping it spinning instead of letting it slow down and lock. But resonances are delicate. They require precise timing, and in the messy gravitational environment of the Pluto Charon binary, they can also lead to chaos. Hydra's spin might not even be constant. It could be wobbling, speeding up and slowing down over centuries, its axis slowly precessing like a top about to fall. Another possibility points to a more violent past. Hydra's irregular, lumpy shape is a clue. If it suffered a significant impact from another Kuiper Belt object long after its formation, that collision could have sent it into a wild tumble, a spin that the system's complex gravity has simply failed to correct. The true story is likely a combination, born from chaos shaped by resonance and forever stirred by the gravitational storm of its double planet. Hydra's frantic spin is more than a curiosity. It is a direct measurement of the forces at play in this miniature solar system. Its rotation holds a fossil record of gravitational interactions, a history of kicks and nudges from its siblings and parents. By understanding why it spins so wildly, we can reverse engineer the stability, or rather the glorious instability, of the entire Pluto system. It tells us this is not a placid, settled place. It is a dynamic and evolving arena where orbits are still settling and moons are still finding their balance billions of years after their violent birth. Hydra's frantic spin is a testament to the forces painting its parent world, and if you could step back to see Pluto from a distance, the first thing to strike you would be its shocking color. This is no monochrome ball of gray ice. It is a world of deep charcoal blacks, rich mahogany reds, creamy beiges, and brilliant, almost blinding whites. This vibrant palette is our 13th mystery, a global canvas where the forces of chemistry and geology are locked in a silent, visible war. The colors tell a direct story of composition. The brilliant whites, like those in the heart of Tombaugh Regio, are vast exposed plains of fresh nitrogen, methane, and carbon monoxide ice. These volatile ices are highly reflective, acting like a clean, frozen mirror. The deep reds and browns, most prominent in the equatorial region of Cthulhu Macula, are the stain of tholins, those complex organic molecules that form in the atmosphere and snow down over eons. The mystery is not what creates these colors, but what decides where they go. Why is this colorful map so starkly divided? Why does one hemisphere look like a freshly iced cake while the other resembles a rusted, ancient artifact? The distribution seems governed by a brutal cosmic logic. Altitude and temperature play the first hand. The bright, white plains of Sputnik Planitia form a vast basin, a low point on Pluto. Volatile ices like nitrogen are gases at Pluto's surface temperatures unless they are under sufficient pressure. In this deep basin, the atmospheric pressure is slightly higher, creating a cold trap where these gases readily condense and freeze, painting the area white. It is a self-reinforcing cycle. The ice increases the reflectivity, which lowers the temperature, which encourages more ice to freeze. But geology is the powerful editor that overwrites this simple climate script. The young, churning surface of Sputnik Planitia is constantly being renewed. Convection cells within the nitrogen ice churn up fresh, clean material from below, while glacial flows cover older terrain. This relentless geological activity acts like a planetary Zamboni, scraping away the dark tholin stain and restoring a brilliant white surface. In stark contrast, the dark highlands of Kuiper Macula are ancient, heavily cratered, and geologically dead. They have sat undisturbed for billions of years, silently collecting the continuous, slow drizzle of red tholin snow from the atmosphere. There is no conveyor belt of fresh ice here to bury the stain. It simply accumulates layer upon layer, growing darker and redder with time. Yet even this explanation has intriguing wrinkles. Some of the color boundaries are razor sharp, following the edges of geological features with unnatural precision. This suggests that the dark tholins are not just falling from the sky, but may also be migrating across the surface itself. Imagine a slow-motion seasonal cycle. When a particular hemisphere tilts toward the distant sun, methane ice on the surface might sublimate, travel as a gas in the thin atmosphere, and then refreeze in a colder region. If that new frost is then irradiated by sunlight, it could transform into tholins right on the spot, darkening that specific area in a targeted way. The varying colors of Pluto are therefore a live diagnostic screen. The bright areas are displays of active internal geology, where heat from within forces its way to the surface and resets the clock. The dark areas are displays of passive atmospheric chemistry, where the slow, patient work of sunlight and cosmic rays writes a billion-year history onto a frozen slate. The map is not random. It is a direct reflection of where Pluto is alive beneath the ice and where it has been sleeping since the dawn of the solar system. What other stories are hidden in the subtle gradients between the rust and the ice? This vibrant color map is not the only cryptic message written on Pluto's surface. Deep within the chaotic, jumbled mountain ranges that border the Great Heart, sharp-eyed scientists spotted something that should not be there. Etched into the icy landscape is a faint but unmistakable shape, a perfect letter X. This is not a trick of pixelation or a random arrangement of shadows. It is a real geometric feature, a crossroads of ridges or fractures that form this precise, angular symbol against a backdrop of geological madness. The X mark is our 14th mystery, a cryptic signature left by processes we are only beginning to decipher. What kind of natural force draws a straight line, let alone a perfect intersection? On a dynamic world, such clean geometry points directly to powerful, organized stresses acting on the ice shell. The most compelling explanation is tectonics. Pluto's crust, primarily made of rigid water ice, is not a static shell. As the dwarf planet's interior cools and contracts, or as the slow freezing of a subsurface ocean expands, the entire crust can be placed under immense global stress. That stress has to go somewhere. It often releases by cracking, creating vast networks of faults and fractures. If two sets of these fractures develop at right angles to each other, perhaps from stresses pulling in different directions over time, their intersection could indeed form an X. This would make the mark a tectonic crossroads, a point where the crust literally gave way along two different planes. But another, more fluid possibility involves the churning convection we see in the nitrogen plains. While the snakeskin terrain shows the polygonal cells of convection in soft nitrogen ice, the water ice crust might experience its own slower, grander version of this process. Upwelling plumes of slightly warmer, buoyant material from deep below could press against the underside of the crust, creating broad, dome-like uplifts. As that dome stretches the surface, it might fracture in a radial pattern. If two such upwelling plumes existed close together, their overlapping fracture patterns could interact to create an X-shaped zone of weakness, later emphasized by erosion or frost deposition. The haunting implication of the X is that it is a surface clue to a subsurface architecture. It is a window into the invisible forces bending and breaking Pluto's frozen shell. Whether from global contraction, ocean freezing, or deep-seated convection, the mark tells us that stress is not randomly distributed. It is focused, channeled, and capable of producing eerily precise geometry across millions of years. This single, simple shape is therefore a profound clue. It hints that beneath the apparent chaos of towering mountains and fractured blocks, there is an underlying order, a hidden skeleton of forces that shape this world from the inside out. What other symbols, invisible to us now, are written into the ice, waiting to be read? That perfect X marks a spot of hidden stress, a fracture in the crust from a world under pressure. But when we look beyond Pluto itself, into the space where its chaotic moons dance, we find a different kind of emptiness. After the New Horizons flyby, scientists carefully scan the space around the binary planet for something they fully expected to see, a faint, encircling ring of dust and debris. Given the violent, impact-driven history of this system, such a ring seemed almost inevitable. Yet the cameras saw nothing, no shimmering band, no diffuse cloud, not even a hint of scattered light. The space was clean, suspiciously so. This pristine void is our 15th mystery, and its implications are profound. In a system born from a cataclysm and populated by tumbling, irregular moons, where is all the debris? The giant impact that likely created Charon would have hurled an immense amount of pulverized rock and ice into orbit. Even today, the chaotic environment around Pluto and Charon is a gravitational shooting gallery where the small moons like Styx and Nix should be constantly peppered by smaller Kuiper Belt objects, generating fresh clouds of impact dust with every strike. This dust should slowly spread out, forming a tenuous, permanent ring. Its absence forces us to consider several unsettling possibilities. The first is that the system is far more efficient at cleaning itself than we thought. The primary vacuum cleaners could be the moons themselves. Their surfaces, especially those coated in bright water ice, might be incredibly sticky, acting like flypaper that captures dust particles upon contact instead of letting them bounce back into orbit. More dramatically, the complex gravitational forces at play might be actively ejecting debris. The chaotic orbits of the small moons could act as gravitational slingshots, flinging dust particles out of the system entirely and into the vastness of the Kuiper Belt. Another, simpler idea is one of time. Perhaps the ring existed, but it was transient. The debris from the initial giant impact may have coalesced into the moons we see today with remarkable speed, leaving little left over. And the current rate of micrometeorite impacts on the moons might simply be too low to generate a visible ring in real time. We might be looking at a system in a quiet period between dusty events. But the most intriguing possibility is that the lack of a ring challenges our very narrative of the system's formation. Could the binary system have formed in a gentler way? While a giant impact is the leading theory, some models suggest a binary could form directly from the collapse of a local cloud of material in the early Kuiper Belt, a process more akin to the birth of a double star than a planetary collision. Such a peaceful origin might naturally result in fewer leftover fragments and less ongoing debris. Or it could mean the impact was of a very specific type, one that produced mostly large fragments that quickly became moons and very little fine dust. This silent, empty space around Pluto is therefore a clue written in nothingness. It tells us that the forces shaping this kingdom are not just creative, but also meticulously destructive. They either never made a mess or they are exceptionally good at cleaning it up. This absence pushes us to refine our models of cosmic violence and gravitational housekeeping, asking us to understand not just how things are made, but how the evidence of their making so completely disappears. The pristine void around Pluto speaks to a carefully ordered system, but that order begins with the most fundamental property of all, the world's own dimensions. For decades, Pluto was a blur whose true size was a matter of fierce debate. Ground-based telescopes and even the Hubble Space Telescope could only give us rough estimates, leading to wild guesses about its composition and nature. Was it larger and icier or smaller and rockier? The New Horizons spacecraft finally settled the argument with a definitive ruler, measuring Pluto's diameter at 1,477 miles. Yet this hard number only unlocked a deeper, more tantalizing mystery. It allowed scientists to calculate Pluto's density with precision, and the result was a profound clue about what lies beneath the ice. Pluto's density is about 1.88 grams per cubic centimeter. That number sits neatly between the density of water ice, which is around 0.93, and rock, which is about 3. This tells us Pluto is not a uniform ball of ice. It must be a differentiated world, with heavy materials like rock and metal having sunk to the center to form a core, while lighter ices rose to form a mantle and crust. Think of it like a cosmic candy with a rocky center and a thick, icy coating. The exact ratio, however, is where the puzzle takes a thrilling turn. Based on the overall density, models suggest that Pluto's rocky core makes up about 2/3 of its total mass, enveloped by a mantle of water ice several hundred miles thick. This layered structure is the foundation for the most captivating possibility in planetary science, a global subsurface ocean. Water, even when mixed with ammonia or salts as an antifreeze, is denser than water ice. If the rocky core is hot enough from radioactive decay, it could keep a layer of that liquid water from freezing, sandwiched between the solid core and the icy shell above. The pressure from the overlying ice also helps, dramatically lowering the freezing point, so the density measurement is our primary evidence that such an ocean could exist. But here is the ongoing enigma. We have never directly observed it. Everything about Pluto's internal structure is inferred from gravity data, shape models, and that crucial density number. We do not know how large the core truly is, how thick the ice shell is, or the precise temperature and composition of the potential ocean. Is it a global sea or just a slushy layer clinging to the bottom of the ice? Is it still liquid today, or has it mostly frozen into a thick, rigid layer? The geological activity we see on the surface, from the convecting glaciers to the possible cryovolcanoes, strongly suggests that heat is escaping. A liquid ocean is the most elegant way to distribute that internal warmth and explain the recent resurfacing. Yet alternative models exist. Some scientists propose that the ocean may have frozen solid long ago, and the activity we see is powered by the lingering heat of a cooling core, slowly leaking out through the ice. Others wonder if the core itself is porous, trapping pockets of volatile gases that release heat as they slowly react. The mystery of Pluto's true size was solved, but in its place, it gave us the far more compelling mystery of its heart. We now know the rough blueprint of this distant world, a rocky center wrapped in ice, but we are left staring at the frozen exterior, listening for the faint, hidden echoes of a possible sea. Is that ocean still there, a dark, salty abyss holding more liquid water than all the seas of Earth? Or are we seeing the last geological size of a world whose inner fire is finally going out? Pluto's internal heat gives it a geological pulse, but its climate is ruled by a far grander and more relentless clock. This distant world experiences seasons of almost unimaginable intensity and duration, each one lasting for decades or even centuries. The reason lies in two fundamental facts of its orbit. First, Pluto's path around the Sun is not a neat circle, but a pronounced ellipse. At its closest approach, or perihelion, it ventures within about 2.7 billion miles of the Sun. At its farthest point, or aphelion, it drifts out to nearly 4.6 billion miles away. This difference is staggering, meaning the sunlight reaching Pluto varies in strength by a factor of nearly 3 over its 248-year journey. Second, Pluto is tilted on its side, much like Uranus, with an axial tilt of about 120 degrees. This combines to create a climate engine of epic, slow-motion drama. The most dramatic consequence of this elliptical orbit is the likely fate of its fragile atmosphere. As Pluto moves away from the Sun after perihelion, temperatures across the dwarf planet begin a long, inexorable plunge. The weak sunlight can no longer provide enough energy to keep the volatile gases in the sky. Scientists predict that the nitrogen, methane, and carbon monoxide that make up the atmosphere will start to snow out, freezing directly onto the surface as frost. This is not a gentle winter flurry. It is the collapse of an entire sky, a global atmospheric freeze-out that could leave Pluto with only a vestigial wisp of gas at its coldest point. This presents a profound logistical mystery. Where does all that atmospheric nitrogen go? The sheer volume of gas that must condense is enormous. It cannot simply dust the entire world evenly. The leading idea is that it migrates to the coldest traps, the permanent shadow zones and low elevation basins where temperatures are lowest. Sputnik Planitia, that vast heart-shaped glacier, is the prime suspect. Its low altitude makes it a natural cold sink, a place where atmospheric gases would preferentially freeze and accumulate over millennia, building the glacier even thicker. This would make the heart not just a geological feature, but a seasonal reservoir, a bank where Pluto's atmosphere is stored as ice for a century or more. This cycle of sublimation and freezing drives the long-term behavior of Pluto's exotic glaciers. Over tens of thousands of years, we can envision a rhythm. During the long, slow summer near perihelion, the Sun, though still weak, provides enough warmth to sublimate nitrogen ice from the heart. This gas enters the atmosphere, puffing it up, and may then be transported by winds to fall as frost on colder, higher ground or on the opposite hemisphere. Then, as the great winter deepens, the flow reverses. The atmosphere condenses, snowing back down primarily into the basin, causing the glaciers there to advance and thicken. The polygonal patterns in Sputnik Planitia could be the frozen footprints of this slow breathing, the convection cells within the ice responding to the immense weight of newly deposited frost. The bladed terrain of Tartarus Dorsa, with its towering methane ice ridges, might also be a product of these epic climate swings, shaped by sublimation during warmer cycles and preservation during colder ones. The snapshot New Horizons took in 2015 is therefore a single frame from a movie millions of years long. We caught Pluto roughly a quarter century after its last perihelion, perhaps in a phase where its atmosphere was still relatively robust but beginning its long freeze. We have no idea what the world looks like at aphelion in the depth of its winter. Does the Heart Glacier expand to cover half the planet? Does the haze completely vanish? Do the colors change as different ices are exposed? Modeling these cycles is a monumental challenge because Pluto's climate is coupled to its geology in a feedback loop we are only starting to understand. The distribution of dark tholins affects how much heat the surface absorbs, which influences sublimation rates. The churning convection in the glaciers themselves moves heat and material, which alters the local climate. It is a complex, world-sized system that operates on a timescale longer than human civilization. The mystery of Pluto's seasonal extremes is ultimately a mystery of prediction. We have seen one moment in its long life. To understand the whole story, we must learn to read the clues in its ice and imagine the world it becomes when the sun is just a particularly bright star in its perpetual night. Flowing down from the rugged highlands and into the smooth, bright plains, the glaciers carry strange, dark secrets. Across several of these icy rivers, particularly where they spill into the great basin of Sputnik Planitia, New Horizons spotted long, slender streaks of deep, shadowy material. They snake across the pale nitrogen ice like veins of charcoal, sometimes running parallel for miles before fading or merging. These are not shadows from mountains or random discolorations. They are distinct features, our 18th great mystery, and they offer a rare chance to watch Pluto's geology in action, to see how its surface and its moving ice are constantly changing each other. The question is simple: what are these dark streaks? Two compelling and very different possibilities emerge. The first is that they are cargo transported across the landscape. As the nitrogen ice glaciers flow, they scrape against the water ice bedrock of the mountains, picking up and carrying along fragments of dark, tholin-stained material. This debris, once liberated, gets stretched and drawn out into long lines by the glacier's motion, like pulling a strand of dark taffy. If this is true, then the streaks are a direct tracer of the glacier's flow path and speed, a frozen record of its journey from the highlands to the Sea of Sputnik. The second possibility is more structural. The streaks might not be deposits on top of the ice, but openings within it. As the glacier moves and stretches, it could develop deep cracks and crevices. These fissures would expose the darker, older layers of ice beneath the bright, fresh surface frost. From above, a long, linear crevasse would appear as a dark streak simply because we are looking into a shadowy hole, not at a dark substance. Each explanation paints a different picture of the glacier's behavior. If the streaks are transported debris, it tells us the ice flow is powerful enough to entrain and carry significant rocky material, acting as a true geological conveyor belt. It suggests a constant sandpaper-like erosion of Pluto's mountains, slowly grinding them down and painting their remains across the plains. If, however, the streaks are crevices, it reveals a glacier under tremendous stress. The ice is not flowing placidly like honey. It is cracking and fracturing as it moves, indicating shifts in slope, underlying topography, or flow velocity. These hidden tensions could point to an active, even violent, glacial environment beneath the serene, smooth surface. The true answer likely involves both processes. Some streaks may be debris, while others are cracks, and perhaps many are a combination, a crevasse that then collects wind-blown or water ice tholin dust, making it even darker. Their very presence confirms that these are not static sheets of ice. They are dynamic, fractured, and dirty, interacting with their surroundings in complex ways we are only beginning to map. By studying their patterns, their distribution, and how they change over just a few miles, scientists can begin to reverse engineer the forces shaping this frozen world. They are the brushstrokes in a painting that is still being made, each dark line a clue written in the slow, relentless language of ice. These dark glacial streaks trace a story of movement and stress, but when you step back to view the entire world, a far grander pattern emerges. Many of Pluto's most dramatic landscapes are not randomly scattered. They appear to be aligned, as if drawn by an invisible hand. The vast western lobe of the heart-shaped Tombaugh Regio, the nightmarish bladed terrain of Tartarus Dorsa, and even several major mountain ranges all share a rough north-south orientation. This subtle but pervasive coordination is our 19th great mystery, and it points to something profound. Pluto may have been stretched and sculpted by global-scale tectonic forces. On a world we once thought was geologically inert, entire continents of ice seem to have been rearranged according to a single, hidden blueprint. Such a planet-wide alignment cannot be a coincidence. It suggests that the entire crust of Pluto was subjected to immense directional stress, cracking and buckling along a preferred axis. The question is, what could possibly apply that kind of stress to a small, distant world? Scientists are investigating several powerful suspects. The first is the relentless gravitational pull of Charon. As the binary partner locked in its eternal dance, Charon's tidal forces would have created a permanent bulge on Pluto, a kind of frozen tidal lock. Over eons, as the system evolved and the orbit settled, this could have strained the crust along a specific orientation, much like repeatedly bending a piece of plastic until it develops a weak line. Another, more dramatic possibility is an event called true polar wander. Imagine Pluto as a spinning top. If a massive weight, like the enormous nitrogen glacier filling Sputnik Planitia, were deposited on its surface, it could unbalance the entire world. To regain stability, the dwarf planet's outer ice shell might have literally slid over its interior, reorienting itself so that the heavy basin moved toward the equator. This wholesale shift of the crust would have generated tremendous global-scale tectonic stress, ripping the surface apart along new fault lines and mountain chains aligned with the direction of the slippage. The heart in this scenario would not just be a feature, it would be the cause of a planetary scale rearrangement. A third force could be the slow, churning convection within Pluto's mantle of water ice. If these upwelling plumes of warmer ice were organized into long, linear rolls beneath the crust, like the convection cells you see in a slowly boiling pot of oatmeal, they could push and pull the surface above into parallel ridges and troughs, creating that consistent north-south grain across the landscape. This would mean the alignment is not a scar from a one-time event, but a living signature of the heat still escaping from Pluto's interior. The alignment of these features is a silent argument written across thousands of miles. It tells us that Pluto's history is not just a series of local events, but a coordinated saga where the entire world responded as one. Whether stretched by a moon's gravity, rebalanced by the weight of a glacier, or kneaded by internal heat, this distant dwarf planet bears the marks of forces that think in global terms. What other patterns, invisible to the first glance, are waiting to reveal the next chapter of this frozen world's epic? This relentless resurfacing of the heart is not a minor detail, it is a revolution. The smooth, unblemished plains of Sputnik Planitia are estimated to be less than 10 million years old. To put that into perspective, when the earliest ancestors of humanity were just beginning to walk upright on the African savanna, the surface of Pluto was being completely remade. This time frame is not just recent, it is practically present day in the grand narrative of the solar system. The implications are staggering, forcing a radical rethinking of what it means for a world to be alive. For a small, icy body so far from the sun, this level of youthfulness should be impossible. It screams that Pluto is not a cold, dead relic. It possesses an internal engine, a source of heat and material powerful enough to erase its own history on a regular basis. This constant renewal is the 20th and perhaps most profound mystery, because it points directly to the heart of the world, both literally and figuratively. The leading theory to explain this eternal youth is a hidden, global ocean of liquid water, or more likely, a slushy brine lurking beneath the ice shell. This is not a placid sea. It would be a dynamic layer kept liquid by the decay of radioactive elements in the rocky core and perhaps gently warmed by the gravitational tug of Charon. This ocean would act as a vast thermal battery and a chemical reservoir. As it slowly cools and freezes from the bottom up, it expands. Water ice is less dense than liquid water, so when it freezes, it takes up more space. This expansion would push against the overlying crust, creating stress, fractures, and potentially forcing plumes of warmer, buoyant material upward. These upwellings could reach the base of the nitrogen ice layer in Sputnik Planitia, providing the gentle heat needed to churn the glacier in massive convection cells. This churning acts like a planetary-sized conveyor belt, constantly dragging older, cratered surface ice down into the depths and bringing fresh, clean material up from below. It is a geological fountain of youth powered by the slow freezing of a hidden sea. This concept shatters our old notions of the outer solar system. We once pictured the Kuiper Belt as a deep freeze, a graveyard of primordial ice balls unchanged since the dawn of time. Pluto stands as defiant proof that this is wrong. Activity is not reserved for giant planets and their large moons. It can simmer in the smallest, coldest of worlds given the right internal recipe. The youthful face of Sputnik Planitia is therefore a beacon. It tells us that geological life can persist in the most unexpected places, sustained by secrets held deep within. If Pluto, against all odds, can remain this active, what other seemingly dead worlds in the dark frontier of the Kuiper Belt are hiding similar, vibrant hearts beneath their frozen crusts? Rising like frozen cathedrals along the shore of that churning heart, the mountain ranges of Pluto stand as monuments of pure strength. Hillary and Tenzing Montes, named for the conquerors of Everest, soar to heights rivaling the Rocky Mountains, yet they are built from a material we would consider fragile, water ice. Here in the deep freeze, water ice is not slippery or brittle. It is the bedrock, a substance harder than granite at these temperatures, forming a planetary crust of astonishing rigidity. This presents a stark and beautiful contradiction. Just beyond these towering, immovable peaks lies the soft, flowing expanse of Sputnik Planitia, a sea of nitrogen ice that behaves like slow-moving putty. How can two such different physical realities exist side by side on the same tiny world? The origin of these water ice mountains is our 21st great mystery, and their very existence forces us to ask what exactly the crust of Pluto is doing. One compelling theory is as strange as it is elegant. These massive blocks might be gigantic icebergs. Picture the vast glacier of Sputnik Planitia not as a sheet of ice on solid ground, but as a profoundly deep pool of solid nitrogen. Water ice, while hard, is actually less dense than nitrogen ice at Pluto's cryogenic temperatures. This means chunks of Pluto's water ice crust could literally float on this denser substrate, like continental shelves adrift on a sluggish, frozen mantle. Tectonic stresses or impacts could have broken the crust apart, sending these colossal fragments bobbing and jostling against each other. Their jagged edges thrust skyward to form the mountain ranges we see today. Their alignment along the edge of the basin would then be a natural shoreline, a floating ring of crustal debris. The alternative is a story of brute force from within. These mountains could be the product of massive tectonic uplift, where global stresses in Pluto's shell have pushed entire sections of the crust upward, folding and fracturing them into majestic ranges. This would imply that Pluto's interior was, or perhaps still is, dynamic enough to wrinkle its own skin on a monumental scale. The sheer height of the mountains supports this. They require a crust thick and strong enough to support such dramatic topography without collapsing under its own weight. This contrast is the heart of the puzzle. The flowing glaciers tell us that part of Pluto is soft and malleable, responding to the faintest whisper of internal heat over millions of years. The towering water ice mountains tell us another part is incredibly strong and rigid, capable of preserving colossal structures for eons. This duality paints Pluto not as a uniform ball of ice, but as a differentiated, complex world with a distinct and sturdy skeleton. That skeleton, whether floating or rooted, holds the shape of the world against the relentless, softening pull of time and the strange flow of its own exotic heart. Scattered across the dark, ancient highlands of Pluto, certain craters wear brilliant white crowns. In regions like Viking Terra, these impact sites are not just holes in the ground. Each is encircled by a radiant halo of ejecta, a stark, luminous ring against the rusty backdrop of tholin-stained terrain. These are not mere decorations. They are geological flashbulbs, moments frozen in time when a violent impact punched through the dark veneer and hurled pure, pristine water ice from the hidden depths out onto the surface. The mystery is not their creation, but their preservation. Why have these bright halos remained so dazzlingly distinct over millions, perhaps billions of years? On a world where dark organic snow falls continuously from the hazy sky, these white rings should have been dimmed to a faint gray long ago, buried under the same reddish grime that blankets their surroundings. Their enduring brilliance is a direct challenge, a clue that Pluto's surface is not a passive canvas but an active workshop where competing processes are constantly at work. One possibility is that the halos are self-cleaning. The pure water ice exposed by the impact has different thermal properties than the darker terrain around it. It might be more reflective, staying colder and potentially causing any atmospheric methane or nitrogen to condense as a bright frost on the halo itself, effectively giving it a fresh coat of white paint with every seasonal cycle. Alternatively, the answer could lie in the whisper-thin atmosphere. While Pluto's air is incredibly tenuous, it is not entirely still. There may be just enough wind to scour loose, dark tholin dust from the smooth, hard-packed surface of the ejector blanket, while letting it accumulate in the rougher, porous terrain beyond the crater's rim. It is a form of natural discrimination where the landscape itself decides what stays clean and what gathers dust. Or perhaps the process is even more subtle, involving a kind of atmospheric chemistry we have yet to understand. Could there be very localized precipitation, where gases in the atmosphere interact with the freshly exposed water ice in a way that actively breaks down or repels the dark tholin particles? Each bright halo is therefore a controlled experiment, a natural laboratory where we can study the battle between contamination and cleansing. They tell us that the dark stain spreading across Pluto is not an inevitable fate. It can be resisted, held at bay by the physical and chemical character of the ice itself. By understanding why these craters shine while the land around them sleeps in shadow, we learn the rules of this distant world's ongoing transformation. What other bright, defiant features are waiting to be found, holding the secret to how a planet manages its own complexion? Those bright, preserved craters are windows into Pluto's past, but they lead us to an even grander question about its very identity. Beneath the active glaciers and potential oceans, we are forced to ask if Pluto is a living world or a perfect fossil. This is the mystery of Pluto as a planetesimal relic. Is this distant body a pristine time capsule from the solar system's violent birth? A chunk of primordial ice and rock untouched for 4.5 billion years? Or has it been cooked, churned, and transformed into something entirely new, its original form lost to a hidden geological fire? The evidence pulls us in two opposite directions. Its location in the Kuiper Belt, that vast reservoir of icy leftovers beyond Neptune, screams that it should be primordial. These are the building blocks that never became planets, the raw materials of the solar system preserved in a cosmic deep freeze. We expected Pluto to be a static, cratered museum piece, a simple ball of ice with a story written only by external impacts. Yet everything New Horizons showed us argues fiercely against that. The churning heart, the flowing glaciers, the towering mountains of water ice, and the potential for a subsurface ocean all point to a world that has been profoundly processed from within. Geological processing requires energy heat to melt, to convect, to fracture. A simple, untouched planetesimal should have exhausted its formation heat eons ago. So if Pluto is processed, where did that enduring energy come from? Is it a unique anomaly, a cosmic accident with a secret furnace? Or is it revealing a truth we missed about the entire Kuiper Belt? The answer rewrites the story of our solar system's outskirts. For decades, we imagined the Kuiper Belt as a quiet, frozen attic. Pluto's vibrant activity suggests it might instead be a dynamic frontier, where many of these icy worlds could harbor similar internal heat from radioactive decay, past giant impacts, or the insulating properties of thick ice shells. Perhaps planetesimals are not inert stones. Maybe, if they are large enough, they can retain enough warmth to differentiate into core, mantle, and crust, and to sustain geological life for billions of years. Pluto, then, would not be a relic but a prototype. It shows us that the boundary between a dead comet and a living world is blurrier than we thought. A world does not need the fierce gravitational kneading from a giant planet to be active. It can generate its own slow, persistent heartbeat. This transforms the Kuiper Belt from a graveyard of fossils into a realm of potential worlds, each with its own hidden history of ice volcanoes, subsurface seas, and evolving landscapes. The mystery of Pluto's nature is therefore a question about abundance. Is it a lonely king in the dark, or the first example of a whole class of active, complex dwarf planets we are only beginning to discover? The next time we send a probe to a distant ice world, what other frozen hearts will we find beating in the silence? That persistent, hidden energy within Pluto does more than shape its surface. It reaches out to touch the very fabric of space around it. As the solar wind, that relentless stream of charged particles from the sun, races outward at over 1 million miles per hour, it encounters a tiny, unexpected roadblock. Pluto, with its wispy, extended atmosphere, should be a trivial obstacle, a pebble in a river that the solar wind simply flows around with barely a ripple. But the data from New Horizons revealed something startling. The spacecraft's instruments detected that the solar wind was being dramatically slowed, diverted, and heated in a region of space much closer to Pluto than any model had predicted. This is our 24th great mystery. How does this faint world punch so far above its weight, creating a protective bubble in the supersonic flow of space itself? The interaction is a delicate and violent dance. Pluto's tenuous atmosphere, particularly its high-altitude haze of tholin particles, is constantly being stripped away by the solar wind. But as those particles are ionized, torn apart into charged fragments by the sun's radiation, they create a weak but significant magnetic field and a zone of charged gas called an ionosphere. This ionosphere is the key. It acts as a conductive barrier, a kind of planetary scale shield. When the solar wind, which is also made of charged particles, slams into this barrier, it cannot simply pass through. It must slow down, pile up, and be deflected around the obstacle, creating a bow shock and a long, trailing wake, much like water flowing around a rock in a stream. The profound puzzle is the scale and intensity of this interaction. Based on the thinness of Pluto's air, scientists expected this bow shock to form very far from the surface, a gentle, wide deflection. Instead, New Horizons found it occurred remarkably close in, and the solar wind plasma was significantly heated in the process. This means Pluto's ionosphere is far more robust and extended than we ever imagined. What unseen process is pumping so many ions into space around this dwarf planet? The answer likely lies in that complex atmospheric chemistry we see in the glowing haze layers. The continuous production of tholins high in the atmosphere may be providing a steady stream of large, complex molecules that are easily ionized by solar radiation, creating a denser and more effective plasma shield than simple gases like nitrogen or methane could alone. Another possibility involves the escape of material from Pluto's potential subsurface ocean. If trace amounts of salts or ammonia are venting into the atmosphere from cryovolcanism or through cracks in the crust, they could vastly enhance the ionosphere's conductivity. This interaction is not just a local curiosity, it is a masterclass in space physics. Understanding how Pluto, a small body with a vanishingly thin atmosphere, carves out its own niche in the solar wind is crucial for interpreting the behavior of countless other objects. It applies to other dwarf planets in the Kuiper Belt, to distant moons with tenuous atmospheres like Neptune's Triton, and even to comets as they plunge toward the sun. It shows us that a world's influence is not defined by its size alone, but by the intricate chemistry of its sky and the stubborn persistence of its internal processes. Pluto teaches us that even at the edge of the solar system, a world can stand its ground against the star that gave it light, holding a fragile piece of space as its own. Pluto's ability to carve out its own space is a testament to its complexity, but it also highlights the frustrating limit of our knowledge. We have seen only one face of this world captured in a single, fleeting moment. The grand finale, the 25th and ultimate mystery, is not about what we have found, but about everything still hidden in the dark. What will we discover when we finally go back? The New Horizons flyby was a brilliant, breathtaking reconnaissance, but it was just at a high-speed pass by a world that demanded we stay. It mapped in detail only the hemisphere that was sunlit during that brief encounter, leaving nearly half the dwarf planet in permanent shadow from our perspective. We have no clear images of its far side, no long-term monitoring of its epic seasons, and no way to confirm the existence of that tantalizing subsurface ocean. The future of Pluto exploration hinges on the next essential step, an orbiter. Imagine a spacecraft that does not race past but settles into orbit, circling Pluto for years. Its instruments could perform feats of discovery that are currently only dreams. A powerful radar could penetrate miles of ice, sending back the first direct echoes from a potential liquid water ocean, mapping its depth and extent. Spectrometers could watch the slow-motion drama of the seasons unfold, tracking how ices migrate, how the atmosphere collapses and reforms, and how the colors of the surface shift over decades. We could stare for months at the enigmatic Reitmans, watching for any faint plume or thermal signature that would confirm it as an active cryovolcano. We could map the entire chaotic dance of the small moons in precise detail, understanding their tumbling rhythms and strange compositions, and we would finally see the other side, the hemisphere forever turned away from Charon, to learn if it holds another vast heart, a different arrangement of blades and glaciers, or landscapes we cannot yet imagine. The biggest mystery is what we have not even thought to look for. Every time humanity has gone from a flyby to an orbiter, from Mars to Jupiter's moons, our understanding has been utterly transformed. We found volcanoes on Io, subsurface oceans on Europa, and lakes on Titan, not because we predicted them perfectly, but because sustained observation revealed them. At Pluto, the same revolution awaits. The true nature of this world, whether it is a solitary wonder or a prototype for countless active dwarf planets, will only be revealed through patience. The next mission will not just answer our current questions, it will unveil new puzzles, phenomena we lack the vocabulary to describe because we have never seen them before. The ultimate secret of Pluto is waiting for us to return, to listen not for a single heartbeat, but for the long, slow rhythm of its frozen, living soul. Pluto's final secret is that it has rewritten the story we tell about our own cosmic neighborhood. We began this journey thinking of it as a demoted footnote, a lonely ice ball at the edge of everything. We end it knowing it as a world of astonishing vitality, a place where glaciers flow in deep freeze, mountains of water ice tower over plains of churning nitrogen, and a hidden ocean may still pulse with latent heat. The 25 mysteries we have explored are not isolated curiosities. They are interconnected threads in a single, breathtaking tapestry of a world that refuses to be simple or silent. The youthful, beating heart of Sputnik Planitia, the possible cryovolcanos building mountains of ice, the dark organic stains holding life's precursors, the chaotic dance of its moons, each one challenges our old definitions of what a small, distant world can be. Every answer the New Horizons mission provided seemed to unlock two deeper, more profound questions. Solving the mystery of its atmosphere revealed the puzzle of its missing ring. Understanding its flowing glaciers pointed directly to the enigma of its internal heat. This is the true nature of exploration. We do not simply check boxes on a list of facts. We peel back layers of a cosmic onion, each revelation more complex and wondrous than the last. Pluto stands as a defiant monument to that complexity. It proves that geological life is not reserved for the warm, large worlds close to the sun. It can simmer in the deepest cold, sustained by radioactive decay, tidal forces, and the stubborn resilience of matter itself. So as we leave this distant kingdom for now, let the questions linger. Which of these mysteries captures your imagination the most? Is it the hidden ocean that might still be liquid, the perfect X etched into the ice, or the haunting bladed terrain that looks like a dragon's spine? Share your thoughts below. We are all explorers here, piecing together the story of a world we have only just begun to know. If you want to journey to more cosmic enigmas, be sure to subscribe. And the next time you look up at the night sky, remember that out there, in the silent dark beyond Neptune, a tiny world with a giant heart is slowly turning, keeping its secrets and forever challenging what we think we know. Keep looking up.